Alright, so I have updated the notebook and I wanted to show you some of the new items. I wanted to support any of the teams that wanted to try to do transitions, so I've done an example that you can use and leverage that, but I don't expect everybody to accomplish this. For the assignment, we're just going to expect you to show that you can control your vehicle in hover and control it in cruise. Here, for the ground simulation, I'm using Nuller Mead still. You can see that it's simulating properly. For the hover trim, I've switched it to using SLSQP method, which allows constraints. So instead of using the cost function to drive basically our dynamics to force and moment balance, you can set the constraints to do that. For the hover trim, this is a little bit overkill, but it comes in to play for transition where I wanted a little bit more powerful optimization routine there. Okay. Now this is enabling the autopilot for roll, pitch, yaw, altitude, and it also does auto gear deployment with the gear enable switch. Then we can look at our motor outputs and make sure that we're not saturating anything. You can see that they're all pretty high, around 80–90%. This is the step response in altitude. Okay, for transition, I've written a piece of code here that takes your velocity, your flight path angle, and the acceleration that you would like, and it calculates and does a constraint that enforces that you're meeting the acceleration vector that you've specified. So this ties back to the lecture on the transition corridor. If you run this, you can specify that you want gamma 0, acceleration 0 for your various flight velocities, and this will give you basically your trim conditions for your aircraft for steady level flight, and that's what I've done here. So trimming at 10 feet per second, 0, and then it spits out theta elevator throttle that you can use in gain scheduling and setting your trim for various points of flight. Now for this piece of code, I've actually set it to 0.1 acceleration. So this is going to be used for actually doing the transition. And I have a flight path angle of 10 degrees. So it computes these points. And now I'm going to fly that. Now, these are showing each transition point, and if you get an odd behavior where it basically drops out of the sky, it's something with the fuel flow, at least on, like this. And I put a warning that says low fuel restart simulation. If you restart the simulation, it's fine. So watch out for that error. I think it might be something specific to the F-35, or it might be a bug in the JSBSim code. But if you get a good simulation run, basically for the accelerations, it looks like we're kind of catapult launching the vehicle because we're given an acceleration, then it kind of reaches steady state. So these are kind of various catapult launches from 10, 100, 100, 200, 300 feet per second. Now that we've got all these transitions figured out, we can do cruise flight. So this is the cruise of the aircraft. Now that we have cruise flight, we can enable the cruise autopilot. I've set this up and you can look at the loop closures. It's just PID control. The heading error, so I'm going to command a heading of 260 degrees, and we're currently 280 degrees, so that's a 20-degree heading error. That's translated into a bank angle command for the aircraft. And since the roll autopilot's enabled, it's going to follow that and try to take the aircraft at 260 degrees heading. So you can see we start at 280 degrees, it banks, and then it comes to 260 degrees. Okay. Now, the next part is the coolest part. I've written, in the simulate function, I've updated it so that you can have conditions, a print statement, operating point, and the condition that triggers the operating point change. And this should give us a full flight of the aircraft from takeoff to a conventional flight. So it says operating point reached hover. Then once it gets to 10 feet per second, it'll trigger this condition. It says operating point reached 10 feet per second. And then it's loading that operating point that we've calculated earlier with the acceleration. So the velocity is increasing, which is what we want because this actually helps us with our transition. As soon as we get to 50 feet per second, it triggers the next operating point, and so on. And you can see that the thrust, I've actually hooked up the animation. So if you want to look in the code and see how to tie this, I've tied everything into the spoiler deflection. So spoiler deflection tells flight gear how to set all the models' rotation, and that's what I've done here. Okay, so now we're at 100 feet per second, 150 feet per second. I tell the fan doors to close once the spoiler deflection angle is above a certain value. So that's how the animations work on that. 200 feet per second. So now we're getting, fully conventional flight. We still have a small angle here, but we're about to kick that off. And then 250. And this looks like pretty conventional flight. So now we've got 300, 400, 500, and 600 feet per second are the last equilibrium points for us to hit. And all these are actually set up for a 0.1 acceleration. So we're actually going to blow past 600 feet per second. So 340, 350, 600. So I think this is knots over here. Got 350 knots. So 600 feet per second, and that's the end of our simulation. Now we've got this log of all of that you can look at. You can look at your flight path angle and things of interest. For control design, when you guys are doing this for your own aircraft, you can use these linearization routines, and you can look at how I've done this here. I've talked about this in lecture, but it shows you how to get this transfer function. Notice that in here I've linearized in the radians because that's the only state available is pitch rate in radians. So I had to do a radian to degree conversion because I wanted it in degrees for what I'm doing below. Then I get all the root locus, step response. This is the input, so I'm looking for input saturation, gang of 4, and Nyquist plot. Same thing with roll, and these should help you get a decent value for your aircraft, but you also have to kind of worry about saturation. I note on here for the yaw, for the F-35B, my yawing of the motors does not work, so I don't have any yaw control until the rudders get enough dynamic pressure to kick in. Here is the root locus, step response, input. You can see this is showing input saturation. It goes beyond the 0.1, which I wanted, but I think in the code it's actually set up to be okay for 0.1. So I will upload this and show it to you guys. I want to briefly kind of go over the XML file so we can look at that. So updates to the XML file. At the top, I've put properties. These control the autopilot. Enable roll loop is set by roll enable pitch loop, etc. Auto gear deployment. If you set AP gear enable, it will automatically raise and lower the gear based on the altitude above ground level. Engine roll mix. These are, you've already seen these. Heading error to bank angle command. This is basically what controlled the ability to set the heading of the aircraft. And let's see, KP roll, KD roll. These are the values that you'll be designing for your aircraft. Aileron trim, elevator trim. And basically I got this from that table of trim values, and I can figure out the trim elevator for steady level flight. Here I've got throttle trim, so trim throttle for steady level flight. Thrust angle trim, and that's basically it. And here's the spoiler table. That's basically the variable that I'm sending to flight gear to control the animations. The gear deployment, and you have a roll channel. So I'll look at one of these channels. The roll channel says can take the heading error, which is the subtraction of the heading command, minus the actual heading of the vehicle. Once you have the heading error, you're going to send that into a pure gain here, which is taking the heading error times phi degrees command. So this basically converts the heading error into a bank angle command, which I limit to minus 30 to plus 30 degrees. Once I have the bank angle command, which is right here, I can subtract the actual bank angle and I get my roll error. Once I have roll error, I can send it into the roll error PID. The roll error PID just has a P gain and a D gain, and I've limited it to minus 0.1 to 0.1. This is normalized aileron deflection, effectively. Then it sums with the aileron trim, which is 0 for this aircraft. And let's see, this last part, this adds the trim. This last part is a switch. It says the value of AP aileron command normalized will either be the manual input from the pilot, FC aileron command norm, or the autopilot calculated roll auto. And roll auto is just what's calculated out here with the sum of the trim input and the autopilot PID. The pitch axis is the same, the yaw axis is the same, so that should be pretty clear. And feel free to ask me any questions in office hours.